Thank you very much, Daniel. Thank you very much for inviting me to this workshop. I'm really looking forward to this week. So I will talk about localization of multiscale problems, and I will talk about something that we call the localized orthogonal decomposition method, which has been developed during the last 3-4 years in collaboration with Daniel Petersheim. That's the first half of my talk. And then the second half of my talk will be about ongoing research in collaboration with my PhD students Fredrik and Anna in Uppsala and Göteborg, Sweden. Okay, so the applications I'm interested in it's a lot of similarities with Yalcin's talk. This is also about multiscale methods. So we're interested in solving partial differential equations numerically that has data that varies on non-separated scales. So it could be composite materials or flow in a porous medium, for example. So I would start with an elliptic model problem and then talk about this local orthogonal decomposition method that we've been working on. Then I will talk about something that Yalcin also mentioned, the high contrast problem and channels, structures, which is a difficult thing for these multiscale methods, also for our method. And then in the end, if I have time, I will talk about some applications to go beyond the elliptic model problem, and then finally present some conclusions. Okay, so we start with the Poisson equation. We have a diffusion coefficient capital A, which varies rapidly in space. We have a right-hand side, which is assumed to be an L2. For the theoretical results I will present. Homogeneous Dirichlet boundary conditions could be replaced by mixed boundary conditions, but it's a bit simpler to present the material with homogeneous Dirichlet. There is a bound on the diffusion from below and above, with alpha and beta, real numbers. And I will talk about high contrast later on, and high contrast means that beta divided by alpha is a big number. This is an important case in many applications. So to introduce some notation, I have the bilinear form A defined in this way. And we seek for a solution in the Sobolev space V, which is H1, 0. So V is H1, 0. So this we have a weak solution by the Lax-Milgram lemma. And we will also have a finite element approximation, which works as a reference solution. So this is will be sort of the thing we want to approximate, but we want to compute that in a cheaper way. VH will typically be the P1 finite element space, so piecewise linear continuous functions. Yeah, so that's a reference solution. So if we would have a smooth solution, U in H2, we would have an error estimate for the standard finite element method in energy norm defined like this. So the gradient weighted with the diffusion in this way, which will give us linear convergence in the mesh sites H. But we will have these second derivatives of U, which typically depend on derivatives of the data. So this will be a big constant. It also depends on the contrast, but this thing will really be bad in multiscale applications. So for example, if we would have periodic data with a period of epsilon, then this fine scale mesh size would have to be smaller than epsilon to get an accurate solution to the problem. And what we want to do instead is to find a subspace, a multiscale space here of VH, for which the corresponding Galerkin approximation is close to the exact the reference solution. We want this error to depend on the capital H, which is a coarser mesh size, so capital H is bigger than small h, but we want to get rid of the dependency of the derivatives of A in this constant. And typically then so we want this to be of the same size as the error for the finite element approximation UH. So we get the solution of similar quality as the reference finite element solution, but the space that we need to, so the matrix need to invert should be much smaller than the matrix for the finite element approximation. Okay, then we want to show first the existence of such a thing, and then that you can compute this by local, a basis for this by local parallel computations. I will talk about that in detail. And then later on we want to demonstrate that using this space for solving PDEs is efficient, in particular if we can reuse the basis many times. For example, in eigenvalue computations or solving time-dependent problems where we iterate and we can reuse the basis many times. If we just want to solve one Poisson equation, it's these kind of methods. It's probably difficult to beat competing methods. Also, we'll talk. There are also semilinear applications where it's useful where you have iteration and also systems of PDEs. Okay, so that's the goal. So now I will introduce this technique that we call LOD. There will be 2 other talks in the workshop related to this, and I think it is tomorrow, perhaps afternoon. So that's, I think it's worth spending a little bit of time on doing this carefully. So we call this multiscale decompositions. We start to introduce some notation here. We have a coarse mesh script T with the mesh parameter capital H. We have a P1 finite element space on this mesh that we call V capital H. Then we have an interpolation operator which maps the H1 space into this discrete space. And I will talk quite a lot about interpolation operators because they turn out to be important for the high contrast problem. But for now you can think of Clément interpolant, for example. You cannot think about the nodal interpolant because the nodal interpolant is not defined on the H1 space. But something that takes averages around a node, or a Scott-Zhang interpolant, for example. Okay, so we have these things, and then we construct VF as the kernel of the interpolation operator. And this is the fine scale space. And then we can decompose our space into the coarse finite element space and this new fine scale space using this interpolation operator. And just to give an idea what functions in these 2 spaces look like, we solve the Poisson equation with this diffusion, right-hand side 1, and then just take the interpolation of the solution, and you get something piecewise linear, continuous. And so that the rest that comes in this fine scale space is something that oscillates around 0. So when I talk about functions in VF, you can think about something which oscillates around 0, like this. Okay, so now comes the simple idea of this local orthogonal decomposition, that we want to choose the space VH in a different way. So we introduce this fine scale projection Q. So Q acts on a function, a coarse scale basis function, and QV is in the fine scale space, so it's something that fluctuates around 0. And we define it in this way. So seek for Q as the projection of V onto the space VF using the bilinear form as the scalar product. And with Dirichlet boundary conditions, this induces a scalar product. It's symmetric also, if we assume that diffusion is symmetric. Okay, so this VF is a closed subspace of a Hilbert space. So and A is coercive and bounded, because we have assumed this on this diffusion coefficient, that it's bounded from above and below. So this object exists for that reason, and we now construct a new decomposition. We keep the same VF as before, but instead of picking V capital H, we pick this multiscale space, which is defined as the old space minus this projection. And so if we move this, the right-hand side to the left-hand side, so to speak, then you see that V minus QV is orthogonal to VF. So the new basis functions, these members of this space are orthogonal to VF with respect to the scalar product, which is problem dependent, used by the problem we look at. If we do the same example again here and we then compute the contributions in the two new spaces, you see that you get much more of this true solution in this multiscale space and very little remaining in the VF space. If you pick the interpolant in a specific way, and if you assume that the right-hand side F is in the finite element space, so it also has to assume that it's 0 on the boundary, you would actually get nothing here. But in general, you get something here which is small. Okay. So now we have this sort of abstract space that exists. I haven't said anything about how to compute it, but given this space, we can construct Galerkin approximation. So we seek for a solution in this space to the original problem, like that. And one can very easily see that this is a good approximation of U because of this orthogonality that that defines it. So first of all, we note that the difference between these two, UF, is in the space VF, because this is the projection of U onto this multiscale space, and we have this orthogonal decomposition of V into V multiscale and VF. So the remainder will be in VF. And then if we look at this remainder, this error, we can immediately add the multiscale part here in the left slot because of the orthogonality between functions, MS functions and UF functions. So you get this equality, and then you can use the equation to go here. And then we use the second property now of the space VF. It's defined as the kernel of the interpolation operator, so this is 0. You can subtract that, use Cauchy-Schwarz, and then interpolation estimate to get up to the derivative of VF again. You get the H out, and then we have to pay with 1 over square root of alpha to go to the energy norm again. So you get the H, sort of the linear convergence rate, without taking second derivatives of U, and that's why we don't get this derivatives of the diffusion popping up. Okay. But for this to be useful, of course, we need to compute the basis for this space, and that's the next step. Okay, so we introduce this set N of the interior vertices of the coarse mesh. So the nodes of the finite element mesh. We let phi x be this function, that's the classical tent function, finite element basis function. And then Q of phi x is the fine scale correction. So we build up the basis of the multiscale space by starting with the basis for the coarse finite element space, and then we add the corrections like this. Then we get the basis for the multiscale space. This is an example of what it can look like. Classical basis function minus the correction associated with this basis function, which you compute then by plugging in the basis function here instead of V. So you get something in the right-hand side there. You get this correction, and then they together form the new basis function, which has the better property. They are not local anymore, because these problems are solved on the entire space VF, and that lives on the entire omega. So they're not local, but they decay quickly, as you see, hopefully in the picture. And if we look at this picture from above, you can also see that they decay quickly in terms of the coarse elements away from the center. Okay, so this quick decay motivates us to localize. So we want basically to truncate somewhere around. So we are at node X, and we want to compute the correction around node X. So then we want to truncate, and then it turns out that you can do it in two ways. You can either look at node X and pick a patch, or you can look at the triangle that has one of the nodes as X and make a patch around the triangle. Turns out that it's more efficient to use the triangles you get a better error estimate in the end, and you can also see it numerically that it's better. This was detected by Daniel Petersheim and Patrick Henning a couple of years ago in a paper. Okay, so now we introduce these patches around triangle T. We call them omega T1 for one layer of coarse elements surrounding triangle T, and then so on, 2 layers, looks like that. So now the method we call it localized orthogonal decomposition. So the orthogonal was what I explained before, and now it comes localization. So now we seek instead correctors, and we want to do this in 2 steps. So we want to sum over the triangles T. So we introduce this Q, T, and L is the number of layers. So that measures the size of this space we solve the problem in. We introduce VF of omega TL as all functions that are 0 outside the patch, so that has support on the patch. Okay, and then we define it as before, but in the right hand side we integrate over the triangle T here. And then we sum this up for all triangles. And clearly for a fixed X here, there will only be a small number of triangles for which this is non-zero. And you also have, if you typically would do this element-wise, so for each element there are 3 basis functions that are non-zero, but you can write, if you sum them up you get 1, so then you get 0 in the right hand side, so you really only have to compute 2 of them for each triangle. Okay, but then you can span this localized space now. It's an approximation, an approximation using L layers. If L goes to cover the whole domain, or goes, let's say, to infinity or as much as you need, then you come back to the ideal method. Okay, so that's localization, and then this last step is that we need to discretize the fine scale. It's still an infinite dimensional space, so we discretize it, and we do it using the reference mesh script TH with a small mesh size, and then we think of small h as small enough to resolve the fine scale variations in the diffusion. We have the reference space, P1, finite element space, VH here, and the reference solution, UH, defined in that way. And the fully discrete correctors we simply get by picking the localized ones and just discretizing each patch with a fine mesh. Then you get something computable. We call that space VHF of omega TL. L is number of layers, and this H is the mesh size on the local problems. Okay, and they solve this equation. So now we have computable approximation, and the full multiscale space has 3 parameters now. You have the coarse mesh size, you have the fine mesh size, and you have the number of layers. It's the span of these functions. And then we get the Galerkin approximation in the new space, like that. And we note that the dimension of this space is the same as VH. For each coarse basis function, we compute 1 modification. They have local support, and they with overlap then, depending on this parameter L, how big these patches are. Okay. And then there are some error estimates. First one is the truncation error, which is the sort of most important part. We have this operator Q. I've now summed over the T, so we have QLH. And this is the one where the L is big enough to cover the entire domain. So how much do we have to pay for the localization is what this lemma tells us. Okay, then we can show that this is bounded by some constant times value less than 1 to the power L, where these things are independent of the variations in A, which is nice. What is not so nice is that this high contrast, possibly high contrast, enters in these constants. So we get rid of the A derivatives of A, but not on the contrast in decay. Okay, so given this, we choose L, the size of the patches, proportional to the log of h to the -1. Then this will give us a higher order perturbation if C2 is chosen properly, so we can get an a priori bound of the difference between the multiscale approximation and the reference solution, which is independent of the variations in A and scales with a capital H, which was the goal. And this was done a couple of years ago in collaboration with Peter-Zhang. So some numerical examples. So here we have data, it's a 2D example. It's actually very high contrast data. As you see here. We let the coarse mesh vary from half to 2 to the minus 7, and fine mesh is 2 to the minus 9. And this truncation parameter L is log 1 over H. And then we look at the convergence, and we can see the linear convergence even though it's high contrast. So the theory is pessimistic. It works better in numerics. This is the standard Galerkin on the coarse mesh, which is of course something which is much cheaper to compute. But just to show that it's not the problem which is trivial to solve with a standard finite element on a coarse mesh. This was an energy norm. You can go to L2 norm, then we get H squared convergence, and you can also look at the coarse part of the multiscale solution, and then you get somewhere in between there in L2 norm. So if we go up to 3D, we have an example on cubes and trilinear shape functions. In 3D, we have the implementation with Petrov-Galerkin formulation. So that means that the trial functions are multiscale functions, but the test functions are coarse finite element functions. This was analyzed by Elversson and Ginting and Patrick Henning in a paper from last year. It's also been used by Peter Simon Helmholtz equation, so you get similar error estimates for the Petrov-Galerkin version, but you'll have much less communication, of course, because you don't have to multiply 2 of these basis functions with large support. Then you have to think about storage a bit when you do 3D calculations. If you don't have enough room, you don't want to store all basis functions at the same time. It can take a lot of memory. And it's possible to implement this without storing all the basis functions at once. So you compute the local solution, and then you multiply with the coarse basis functions to get the coarse stiffness matrix. You stand these values up. Then you can compute the multiscale approximation. You get the sort of weights on the basis functions. We can say you get the interpolation of the exact solution. And then you can go back and restore and recompute the local function when you know what this value is. And in that way, restore the full solution without having to store all the basis functions at the same time. And the price of this is not twice as solving the first problem, but so it actually gets cheaper because you know what to plug into the right-hand side of the local problem. So it's in this case, instead of 7 problems per element, you only have to solve 1 when you reconstruct the full solution. So it's a technical thing, but you have to think about this in 3D because it gets quite big. This is just a picture of what the corrector function looked like. This is a project that my PhD student Fredrik Hellman is doing. Okay, and then we pick this random data set like that. Capital H, we only have 3 levels now. Reference mesh is 2 to the minus 6. Of course, it gets quite big quickly. So on a small laptop, we can't have two fine meshes here. L is this log 1 over H again, and we get the same kind of behavior of this is energy norm and this is L2 norm, and this is when you just take the coarse part of the solution. We get somewhere in between. Okay, and then of course there are a lot of competing or a lot of works related to what we do, and there's been a lot of works been done for many years. So I just want to say something about mainly what inspired what we have done, and that was clearly the variational multiscale method, where you split the space up in 2 parts, which we have. Our method is a version of this. Also, the multiscale finite element method that FNDF has been a part of developing, with the idea of viewing this as modified basis functions, and also the idea of oversampling came there. This is maybe less. You don't see this as much maybe in multiscale presentations, but was this work in 2003 on a posteriori estimation by solving local problems on stars, which was the thing which actually inspired us to solve these local problems numerically, and then we increased the size of the patches from stars to bigger things. So I worked on this in my master's, my PhD thesis in around 2004. Then this nice paper, which I got aware of much later, which deals with these Green's functions, so these basis functions and the decay of those. Then there's been a lot of activity going on, and we have the work from 2014, which was inspired by previous works by Bushka and Lipton and this AL basis. And there is work now also on iterative numerical homogenization, which I think we will hear about in the workshop, quite recent. And then the very relevant for this talk, high contrast paper by Peter Simon and Scheichel from last year, which sort of leads into the second part of my talk. And there are a lot of other things that I don't have time to mention. It's quite a lot of work done in this area. Okay, so now we come to high contrast data. So this is now ongoing research. We have a preprint on this. Oh, good. Okay, so it's still the Poisson equation, and we now simplify the problem a bit in order to sort of pinpoint the issue of high contrast. We look at the diffusion, which only takes two values. 1 in omega 1, it's the black region here, and alpha in the other region. And alpha is much less than 1. We have some right-hand side in the numerical examples, which happens to be this function. Okay, so as Yalchin said, there is a problem with these kind of methods when you have channel structures in the data. It leads to non-local behavior, and this whole idea of multiscale methods build on trying to sort of localize the fine-scale computations, and you have communications on that connects sort of distant parts of the domain, which is problematic. And so you can see in numerics that basis functions, they don't decay as well if you have these channels. They start to spread along the channels. And this, of course, if you have a fixed truncation size, it ruins the solution of the multiscale approximation. But it turns out that the choice of interpolant, which I haven't said anything about almost yet, is important in here. And now I write this in a slightly strange way, perhaps, but so the interpolant of V is a linear combination of the basis functions, piecewise linear basis functions, and then there is some average taken here. Could be the Clement interpolant, for example. It could be then the average on a vertex patch. So this is just what I mean by this notation. And I will talk about different ways of taking this average and what effect it has on the decay. Okay, so I have 3 examples with high contrast data. One with these channels, then we have these balls, and then we have this thing which is some generated by some random field. Now let capital H be 2 to the minus 4 and small h 2 to the minus 10. Vary alpha from 10 to the minus 1 to 10 to the minus 6. Then we look at the energy norm error compared versus the number of layers, and that should be an L there, or maybe rather that should be a K. So that's the number of layers, and then see what the effect we have from truncation. And we use the Scott-Zhang interpolant on triangles here, and I'll get back to what that is. Okay, so in all 3 examples, you see that, so these lines are for 0.1, this is 1 divided by 100, and so on. It gets worse and worse as alpha gets smaller, and it's the worst one is this one with these clear channels. But also the other 2 suffers quite a lot from high contrast. So it's clearly a problem. It's quite easy to cook up things where it doesn't work, even though it looked pretty nice on this data in 2D I showed you before this SB data. You can cook up things where it's not very nice, as you see here. Okay, so then now it gets a bit technical, but we have sort of a new interpolation operator which helps in this respect. But before I present that, I need to sort of explain what it comes from, otherwise it will be a sort of a miraculous thing. Okay, so then we have to think about why we don't have decay when we have high contrast. So we go back to the definition of the fine scale equation. These correctors were defined in this way. Vf was the kernel of the interpolation operator. The right-hand side has support on one triangle. So the reason why the solution decays, it's for two reasons. First one, that the right-hand side is localized to one triangle. So the right-hand side is support on one triangle and there's no data outside. So if we would solve the thing in the full space V, it would sort of look like the Green's function in 2D, like logarithmic decay. So there's some decay coming from that. But that's not all. I mean, we showed exponential decay. And the other reason we have decay is that the interpolation operator, so this constraint of being in VF actually, or hopefully, means that the solution itself in the nodes is close to zero. So then you can have the picture of this log function and then it's pushed down in all coarse nodes to be zero. That's what sort of makes this solution decay quickly. And this is what fails in high contrast, that this thing doesn't lead to solution being close to zero. And this is now a heuristic motivation why, and sort of based on our experience in numerical simulation, why it is so. So let now G be the solution of the function on the boundary of the triangle. So we have some data, G on the triangle, and then we have homogeneous Dirichlet condition far out. And then we want to solve this problem, and we view it now instead as the minimization problem, the corresponding minimization problem. So we want to minimize this energy. The right-hand side is zero now because we look outside the triangle. There's no data outside in the right-hand side. So we look at this minimization of this under the constraint that we are in this fine scale space and we have this data. So when you look at this, you see that high derivatives in omega 1, where the A is equal to 1, are penalized. They are very expensive to have here. It's very cheap to have high derivatives in omega alpha, where this alpha is maybe 10 to the minus 6. So therefore, this minimum tries to avoid decaying quickly in omega 1. So if you have a channel, like for example, going out in one direction, maybe you have Neumann conditions over there, then it wants just to stay constant all the time. Or if you have Dirichlet condition, it looks like a one-dimensional Poisson equation, so it decays linearly. Definitely not exponentially. And this hopefully should be cured by this thing then, that it has to be zero in some spots. But if we take an average here in the interpolation operator over omega x, could be a vertex patch, if that includes both omega 1 and omega alpha, these conditions will still allow high values in omega 1, and then in this minimization process you will get big derivatives outside the channel, and then the function will have maybe the opposite sign then, so it still fulfills this, but it fulfills it without being small in the channel. So it sort of preserves this solution from the problem without the space VF. And then everything else is taken care of in the omega alpha region. So we don't get decay. And the only way to get the decay is if the region we integrate over is in omega 1. So if we have this averages taken just inside a channel, because then there is no possibility sort of to compensate for this in omega alpha. So if you think about nodal interpolation, you would like to pick nodes in the channel at some distance. And if you have these averages, you want to integrate just over the part of the channel. Okay, and so we want to construct a method which integrates only in omega 1 to make sure we get decay there. Then we look into this Scott-Zhang interpolation operators, which can be used to do that. So for each coarse node, we have associate a domain sigma x, which we will use for this Scott-Zhang interpolation definition of the Scott-Zhang interpolant. We need a dual basis psi x fulfilling this property, and then over the domain sigma x. And we then define the nodal variable to be the integral over sigma x psi x times v. And this is the interpolant. And then this sigma x does not have to be a full element on a coarse mesh, or a full edge, which is also a possibility, or a patch. It can be part of that, which we will need because we want only to take the part which is in omega 1. The stability of this interpolant, so the L2 norm of this thing, of course will depend on the shape of sigma x, the size of it. If it gets very small, the constant gets big, like the nodal interpolant will be a sort of limiting case. And also its distance to x, but we typically think of that we have a node x inside sigma x, but it would not be totally necessary to do it that way. Okay, so now how do we select this sigma x? So the standard approach before would be to take the entire elements and do this Scott-Zhang interpolation defined on that. Now instead we divide our nodes into two parts. We have the type 1 node, which is the node where the x is in omega 1. If we get one of these, we pick a domain inside this vertex patch, but only the part which overlaps with omega 1. So omega 1 will be the black areas. So in this case it will be this, and we want to have a connected set. So we want to skip this part, because we want to be able to prove a Poincare inequality on this domain with a nice constant. And if we would include this one also, you can have a function which is constant on these two, which makes this 0 but varies in between. Okay, so we want a connected part. The type 2 node is the node that's outside the omega 1. And there we can do, that's not so critical what we do there. You can pick the entire patch if you want to, or as here we have some scaling u delta, so you can pick a smaller one. It turns out in the analysis that we can only prove our sort of local, the estimates which is independent of contrast if delta is less than a half, so it's a little bit less here. But in numerics, it looks like it works to have the entire patch. So it might just be that we're not able to prove it. Okay, and then we assume that so there are sufficiently many nodes of type 1. So if you have this omega 1 distribution of these channels, you have at some certain distance, j times h, there has to be a node that enters in this region. We also want T to be quasi-uniform. So under these assumptions, we can prove this weighted Poincare inequality, which is crucial in order to prove contrast-independent decay with a coefficient which is independent of contrast. And then if we assume a delta is less than a half, we can get this decay results. So so basically if you take k layers out and look at the energy of the basis functions out there, it's less than some gamma to the k of the entire energy. So that's an exponential decay. Where these things are, and I guess beta here is 1 then in this example, so it's independent of alpha, I should say. Okay, so we have a preprint where this is done out just recently. Okay, then this is very much related to what another paper by Peter Simon Scheichel. They had so our approach, since they did this before us, so we are similar to what they did, but with one clear difference. So they have an A-weighted interpolant. So it's also adjusted to this particular data you have. But there instead, PA is a projection on this patch omega 1. This is the vertex patch. So it's sort of similar. It's so we only take into consideration the omega 1 part when we compute these averages. So here you would also take into consideration sort of a neighboring black channel coming. But otherwise it's very similar. So we are very similar to what they already done. Their analysis is not limited to A taking 2 values. But our contribution then is that we have added this freedom to choose sigma x with better Poincare constants. Because the problem of this approach then is that you have to have quasi-monotonicity of A, and that's very hard to get in practice in these examples I have showed. But then also both approaches can be combined. So instead of taking these integrals over omega 1, you can take the integrals over a region where you still have the quasi-monotonicity, and then you get almost the same thing as we have done. We have tested this numerically then, this interpolation operator, Peter-Stein-Scheichel, and this one with quasi-monotone version of it. And in this simple case with 2 values, where you just, if you have 2 black blobs in your patch, you just integrate over one of them and neglect the other one. And then we look at the same examples as I showed before. This is again with the standard Scott-Zhang interpolants. So this picture already seen. This is not a very kind example to the other approach, because you don't have quasi-monotonicity on any of these on that coarse mesh of that size. So we don't expect the Peter-Stein-Scheichel version to work here. But still it works for the first one, but it gets worse for the other 2. So as you remember, these were alpha 0.1, and then it goes up to 10 to the minus 6. So if we take, so our version there, when you just integrate over the black areas, if your node happen to be in a black area, you get this. The decay is actually independent of the contrast, but now this is the entire error of the solution, and then it pops out the 1 over square root of alpha in that process. But you see a sort of clear, it gets much better doing this. And then we can also do this quasi-monotone version of their interpolation operator, and then you get something which is very similar. So and it relates to proving this weighted Poincare inequality. When the quasi-monotonicity is violated, you get bad constants in the Poincare inequality. So you want to get rid of these black areas that are sort of disjoint from the center. Okay, so that was what I had to say about high contrast. The timing, when is it? 5 minutes, okay. Applications then. I think I will very quickly then say something about how to use this basis for eigenvalue problems. So now we have the prototypical self-adjoint eigenvalue problem here with rapidly oscillating data. Okay, weak form, finite element approximation. So the error in eigenvalue you typically get with standard finite element method is h squared if you have smooth enough eigenfunctions, but you get the constant which depends on the variations in the diffusion, as for the Poisson equation. And you have similar for the eigenvectors or eigenfunctions, it scales like h. So it's the same situation that you need to resolve all the oscillations to get good eigenvalues. If we do just the same LOD space as I already introduced, and we use that instead, we can prove H4 convergence for the eigenvalues without assuming more than H1 regularity. This is compared to the reference eigenvalue on the finite element mesh. And this is joint work with Peter-Stein. So it works very nicely for eigenvalue problems, this basis. This is an example where a very coarse mesh, just first mesh we only have this, so it's just one basis function. We solve the one by one eigenvalue problem to get out this. And then we refine once. Then we get 9 basis functions. And we look at the relative error in eigenvalue. We have a reference measure 2 to the minus 7. Then refine once more. Then we get maybe 25. You see the error, relative error converges quickly. So here is the h to the 4 convergence rate. So you can get a lot of. If this would be a smooth, like diffusion equal to 1, you would get much better. It's like h to 6 or 7. Okay, the other application we've been working on is time-dependent problems. So this is parabolic equation. F can depend on time, data in L2. A is assumed to be independent of time, which is important because we compute the basis functions by considering this diffusion. If it changes all the time, then we need new bases all the time, and that will be very expensive. So this is an important assumption. We use backward Euler approximation just in time. Get this expression, the difference quotient, and then the LOD, then just using the same space again and solving this problem with some initial approximation of the initial data. One would expect it works nicely. You get H2 convergence in the L2 norm. We need some regularity in time on the F to do this bound. We still get constants independent of A prime. So we use classical a priori analysis and combine that with the elliptic results for the multiscale method. This term, which looks a bit bad, it's actually also appearing for standard finite element method if initial data is in L2. If the initial data is in H1, 0, if it's 0 on the boundary, you can go down to a half there. If the initial data is in H2, it actually becomes problematic because then we're not very happy with H2 estimates in this theory because then this 1 over epsilon pops out. So that we cannot do. Then we have also looked at semilinear problems, like the Allen-Kahn equation. Okay. And this say again that this case of time-dependent A is not covered because it would require updates of the basis. And then numerically it behaves as the theory suggests as H2 convergence with some small time step here. This is also a preprint with my student Anna Persson. Okay, and then there are a lot of other applications of these works that has come after the first paper in 2014. For example, semilinear problems, semilinear eigenvalue problems, Krosbitevsky and Helmholtz, Petersheim, and you see reduced basis. So quite a lot of activity the last 3 years. Here on time dependent it's less. There's on the wave equation by Syrabul and Patrick Henning. And we have something on thermoelasticity, a system of 2 equations. Then the problem here, so you could think of, so you have a heat equation and you can construct an optimal basis for that equation. Then you have the elasticity with an optimal basis for that one. But the challenge here is that you also have a coupling, which can have multiscale features, which you need to take into account. But I don't have time to talk about that today. Okay, so conclusions. There are a lot of activities on these LOD methods last 3 years. High contrast is challenging, and we think we've gained some insight to this problem and proposed a new interpolant. It works nice for eigenvalue problems and for time-dependent problems. More work is needed on the efficient implementation, even though we've done 3D now, so we are sort of slowly getting in that direction. But I think there are other people also working on that. Thank you for your attention.
Thank you, Axel. Other questions? Concerning the work on the high contrast, in the theorem you have that you need a certain percentage of type 1 nodes. Could you comment a little bit on what you see in the numerical experiments? So do you need that somehow each connectivity component of the channels is actually as a node in the pore space?
So, I mean, my experience is that you need at certain even distances a node entering in the channel. So if you miss the channel all the time, it will just keep on. And I mean, if you have them rarely, the decay will be slower. If you have them at each capital H, it will be the nice exponential decay. So it seems to be the positions of the nodes, this background decay of log, which you don't have in the channel. That I don't think that's so important. It's important is the node placement.
These examples that you showed,
Yeah.
so did you put the nodes
Yeah, I didn't say that. So
the one that you
in this example, we didn't at all match the nodes to. We just placed them randomly. Here they are. Yeah, in these two.
so maybe this is an explanation of the different behavior of the
You mean that you have some alpha? Yeah, but yeah, you're supposed to be 1 over square root of alpha popping out for the full error. I think it's like the standard, it's like just the standard a posteriori or a priori estimate for standard finite element also gives you this constant. Yeah. Okay. Yeah. Yeah. Maybe there is. So it's the theory doesn't say anything about this. Yeah. Yeah. We have looked. So Fredrik has spent a lot of time doing this, trying to understand it. It is fairly complicated. I mean, there are the details that we don't fully understand still, but I think we have a sort of partial understanding of how it works.
Okay. And on the other hand, if you choose the macro mesh just by putting points in the high conductivity regions and then trying to do the Nodal decomposition without having any nodes in the other part, would this be okay?
No, in the other part you have to have it should be quasi-uniform, so they have to be roughly distance h from each other. Yeah.
Further comments or questions?
First, I like both of your talks, and what strikes me is that you're essentially trying to approximate some weird solution or some solution which does not behave very nicely in terms of Euclidean coordinates, and you're trying to find some kind of functional space which is lower dimensional, and for two different reasons. Yachin's reason was essentially that if you believe in homogenization in those cases, you would say that it's close to some two-scale expansion in some sense, and that motivates the...
Just multi-continuum, that's not a...
Yeah, but okay, the first part of the talk where there's no refinement regarding high contrast part. Whereas here it's more like you say that it's close to lower dimensional space because the right hand side is in L2, and so in some sense the width of the solution space is much smaller, and I cannot relate both. And that's always been puzzling me because if you knew, for instance, the second method that your coefficients were periodic, would it improve your locality?
I mean,
I don't understand though, that all we do, like there is an assumption that we have a low dimensional space.
Yeah, but for different reasons. And for instance, in that part where you essentially use elliptic regularity in some sense, the fact that you have this localized basis, which is very surprising from me at the first glance. The reason for that has nothing to do with the fact that your small scale solution will converge to something.
No.
And my question is, if you know on top of this that the solution converges to something, can you even reduce the localization?
yeah.
Really not clear.
We have
Yeah.
we have
Small
a
is not the same.
periodicity, can we do something more? Can this method as it is can give you something?
Yeah, or can you put
Can you put some special feature?
yeah, can you
So I
put
mean,
more if you know more?
There will be a talk tomorrow that partially answers this question and will show you numerical experiment that if there is a periodic situation where you know that homogenization theory applies, then it seems that actually you don't need to increase the L to get better accuracy, but you could put a fixed L, like in the multiscale method. So we've thought about this, and there are very close links to homogenization theory if it is applicable. But I think tomorrow afternoon would be the right
But I
time.
mean, if I have a coarse clock, right? If I know if there is a periodicity, I will look and represent the volume and I populate it. All these methods will be
Of course,
straightforward.
but okay, I agree, but my question was more, if you do that, you
No, but then
change.
otherwise, if you don't know, you have to look at the whole domain. You will still get your periodicity out of it.